It gives me great pleasure to introduce Dr. Sanjay Ghosh, who is with Google, and he has an MTech from IIT Kanpur, and he earned his PhD from the Industrial Design Center at IIT Bombay, where he trained under tuition. After graduating, and I guess even prior to this PhD, worked in a number of organizations such as HP, Samsung, and others, and he's worked contributed to a number of products that have come out of these companies. Many of which are listed in the announcements that went out, and I just want to belabor it. But I think a couple of points that I would like to emphasize: it's got more than 20 great patents in this area, and it's a significant name reckoned with in the HCI domain in the country and internationally. And it's been a while to be sort of talking about identifying dates for him to come and visit us, and we are especially grateful that he can come today, not least because Sanjay is, recently become a father, and I'm sure it's a time of much joy, excitement, and not to mention sleep deprivation. So, on that note, please join me in welcoming Dr. Sanjay.
Thank you, Professor Balaji. That was a very warm welcome, but the introduction was a bit too much. I have not achieved so much in life. There's yet to do a lot of work in HCI space. So really happy to be talking in this theme, in the Samvaad series theme, specifically on design for technology, because I myself, in my career, I was a technologist earlier, as he rightly mentioned in the introduction, and then now I have become a design researcher. So I can speak a little bit with my experience on design for technology. The title of this talk is Decoding Typing on specifically Indian language, and that was my dissertation, my thesis work, PhD thesis, which I did in IIT Bombay. We are still working in that space, but we used a specific method of design, which is cognitive modeling. Not many people speak about it a lot. Whenever you hear people speak about design, they speak about user-centered design and many other methods. This is a less explored field in HCI. So I have divided this talk into two parts. First, let me give some background about cognitive modeling, what exactly it is. I'll speak about some examples as well. And then at the later half of this talk, I'll speak about what we did in research for Indian language, how we apply this cognitive modeling methods into developing something for Indian language. So my attempt here for this talk would be first to all the students, especially researchers, introduce cognitive modeling as a thematic area and as an approach to doing design for technology. All of you are technologists, and therefore it's very important to know all the methods, how you can make technology better for users. This is a complex topic. Sometimes I do lectures on cognitive modeling, cognitive psychology, and generally post-lunch sessions a little bit having an involved topic like this could be difficult. So what I'll do is I'll try to challenge you as well. I'll try to challenge your cognition by some questions and some activities which we can do during this session. So to participate. And in the end, I'll also try and demonstrate how the tool of cognitive modeling and the models can be applied into real-world problem. I'll take a use case, as I said, of Indic language research. Okay, so since we are setting up grounds for technology through design, let me do one thing. I'll play a video, a short video, and you hear out this is a video from Don Norman. He's one of the most influential person, most followed person, a design guru. Let's hear out what he says about designing for technology?
To me, what design really is applied cognitive science. And when people ask me what I am, I say I'm an applied cognitive scientist. And what's interesting about most of the fields in the university is that they're analytic. We're trying to understand. And what design is a synthetic field. It's trying to produce. But it's trying to produce for people, something that, by the way, engineers have completely forgotten. Why are engineers building things? Why are we writing computer programs or building bridges or whatever we do? It's for people. So, shouldn't engineers know something about people? Or at least shouldn't we work together?
Made a very good point, because technology is always for people. It's for users to use. Without users, technology just remains a technology. It doesn't get into working. All of these big companies in Earth today, they have their philosophies. So their number one philosophy. So by the way, these statements are for the philosophies these big companies follow for their employees, for their products, for their existence. The number one philosophy, there is something common across all of these big giants. They speak about their customers, their users, their people for whom they are designing. The usual practice in the industry is to use a term which people use is user-centered design. You must have definitely heard about this term when you speak about design. So what they say is, when you design for people, keep your users in the center, which means you would design an idea, you would implement it through prototype, you would iterate back, you would test with your end users, and again, this is a spiral process. You would again go back and design something new or improve, implement again, evaluate. So this is a spiral cycle. It keeps on going to improve your product. And that is why they call this as user-centered design process. Your user stays always in your mind throughout your product cycle. But and yes, user testing, is a gold standard. Every company, when they launch a product in the market, they would do a rigorous user testing. But there are, again, a lot of weightage attached to it. It takes a lot of time. There is a lot of expenses. Again, there is human sample bias, because you would test your product with a set of samples. You can define your sample in different ways, but again, it is only a limited set of people whom you are testing with. And then there is a limit to how much you would iterate, right? How much test you would do with users. So the point is, isn't that better if we have something in form of user simulators, something like where there are models or there are mathematical models which define how users think, how your people would think, and that is where cognitive modeling comes into picture. What I'm talking about here is, on one side, in user-centered design methods, you would test your product with a limited set of users. Okay. The cognitive modeling approach is again an approach within user-centered design, wherein you create those models early, again, through a lot of data collection, empirical experiments from a bigger set of users, diverse set of users. And once your models are created, you use this as simulation tools to test your products. In this way, I'm nowhere discounting the fact that testing is not required. User testing is not required. User testing is still a gold standard. Everybody does that. Every company does that. This is a different approach, an additional approach, a quicker approach to do testing easily through simulations. By the way, another point which I forgot to mention very early in the talk, although in the introduction he mentioned that I work for Google, but this is an independent talk, a lot of work which I have done independently as a researcher, and this has nothing to do with the views of the company for which I work and the job which I do. So it's different. Don't relate it to something from what is happening in Google. Okay, so here what I'm trying to introduce is a method called cognitive modeling, which is an approach to design technology for users again. So what is cognitive modeling? It's a research methodology wherein it involves design of computer simulations, models, mathematical models, which would represent human cognition and human perception and human behaviors it would attempt to do that. You cannot replicate a human being and their thoughts and their perception at a time, but it would try to, there are ways to attempt to some extent replicate it. But the premise with which it works is that thinking which is going on in humans' mind is kind of computation only, because what's going inside the brain is also what's going inside a computer. Because computers, we know from basic definition, it's input output, processing and memory. We too have that. We too have at all levels. We have a big memory. There are long-term memory, kind of production memory, quick memories, working memories, and then we have our input and output mechanisms, sensors. And there are processors, actuators, our muscle memory, our movement, all of these are controlled by our brain, which has this processor. So if our brain is kind of computer, just like in computers, we can measure things, we can benchmark things. It's also possible to some extent measure and model as well. Our cognition process, our perceptions can be also measured. The good thing is the cognitive psychology, which has been an age-old discipline. Scientists have already done that. A lot of thinking process or different movements which users do, which we do as human beings, have been already modeled. People have done longitudinal experiments to find out how much time it takes to bring out something from our long-term memory to a working memory. That has been defined, that has been, through experiments, it has been proven to some extent. What we are trying to do now is, we try to use the relevant models on our problem statement, on our real world problem statement. Try to see our real world problem statement matches with some of the solutions which are available, and try and match those. That's more of the work which we do in cognitive modeling. Now, as a discipline within computer science or related disciplines, cognitive modeling also overlaps with artificial intelligence, ML, because overall the idea is to have better fairness for people, trying to understand how people would react at different situations and create models or predict things. So it is an overlap. It has an overlap with AI and ML as well. But what are these? What are cognitive models, by the way? And how are these really useful? You can consider, any model for that matter is basically a simplification of some complex phenomena, which you can either have a description in form of a theoretical description or an analogy or a theoretical approach to describe some phenomena, or it could have been mathematical equations. So you can consider models to be basically a continuum. On one side you have theoretical models, and the other side there are very specific predefined set of mathematical models. Within cognitive modeling theory, there are descriptive models and then there are predictive models. We are speaking more about predictive models today in this talk. I'll speak more about the predictive models, although there are a huge number of descriptive models as well. Because few of these examples which I'll show early in this talk, we would use it. We will try to make use of that in the use case later, at the later part of this talk. So this is where we will focus more. Okay. So I'll try to explain few of the models which already exist, so that it's easier to apply them and see how the application of those models happens on real world problems. So basically this is one of the cognitive model which defines how human motor movement performance works. Right? Let's see this video and let's see what is the phenomena happening. He's doing an experiment and he's changing the stimuli in the experiment. Did you see some phenomena here? I guess one of the phenomena we would see is he was changing the size of the targets, and he was also placing the targets at different distances. And because of that, the motor movement which he was doing a very mundane basic task, moving from one source to another destination, basic task which we would do in many different real world situations. We would do these activities, but given the size of the targets change and the distance between the target change, the speed was decreasing or increasing. Again, you would see another phenomena. When he was moving to a smaller target, the time he would take from starting till end, the speed at which he was moving his hand was not constant. He would start fast, but slowly he would slow down and then target on this one. Because in his mind, what he was doing is doing a trade-off between speed and accuracy, because he wanted to hit the target right. If the target is big, he was not worried about that accuracy. He was able to do that faster. So what Fitt's law says is, by the way, the name of the scientist is Fitts, and therefore the law name is Fitt's law. Right? Okay. So what it says is the time to acquire a target is actually a function of the distance and the size of the target. Two variables here: the distance of movement and the size. So through experiments, lot of empirical experiments with different types of user base, he's come out with this model, which is very, very popular to apply on human-computer interaction space. Let's see a few examples of this one. This looks, when Fitts did this experiment, he did it on a physical objects. He did exactly this kind of experiment. But this model which came out can be applied into many other things in the digital world as well. Let's see a few examples. So this is a question for you guys. So what you see here is two interfaces, design of two interfaces. These are mail clients, email clients. On the left you have design 1, on the right you have design number 2. So the question is, just from your heuristics, what do you think, how fast would you be able to compose an email? I mean, which design is better to compose an email, to reach to the button, either compose or new? Which one would be faster? Right. We just saw the Fitt's law, which says the bigger the target is, you can move your mouse screen very quickly to this one. These are big. This is a small. Right. It applies to such kind of things in designing interfaces. Again, when Fitts did those experiments, he did it on physical objects, but those models did carry forward to other scenarios, real world scenarios as well. Let's see a different example this time. Which of these menu positions is more efficient? On the left, you will have there's the old Windows Notepad menu. You'll have file, edit, and the other one is Mac, which again has file, edit. So if you want to press edit, if you want to take your mouse point and point it to edit, and here you take it to edit, which one would take less time? Windows, because the size is bigger. Yes, but Mac people did something different. Here something else is coming into play. It is true that this button size is bigger, but what they are also playing here is, since it is at the end of your screen, so beyond this screen your mouse will not even go. Therefore the size of this one, this button, edit, in Mac, it has an infinite depth. So therefore when you are pointing towards edit in Mac, basically you are not worried about your accuracy, because your mouse will not flow away. You will anyway end in the edit. That's one of the design trick which they have done by applying the same law. Okay. Here again Fitts law plays, but here the size of the button is infinite, and when you have something in your numerator is infinite, then this becomes a big number. So it becomes more efficient in some way. Again a question. There is two types of menu. We have seen many websites, many designs. You have seen list menu and pie menu. Now if I want to select say Tuesday, which of this menu will be faster? circular or... It also depends upon where you are starting though, your homing position. But on a long run, if you have to select this again and again and again and again, they say that circular menu would work faster. Again, because it's bigger targets, distance is small. But remember, it's also the angle with which you are moving. So there are few angles which might be difficult for you to move. Consider this kind of menu on your phone, and consider stroking at an angle of 10 o'clock. So it becomes difficult to move in some angles. So it also depends upon what you are designing. What is your real world problem which you are designing for, and then use those models and see which one is more efficient. Another thing, but will that hold true always? Bigger targets, lesser distance. What if I increase the number of options? If the list becomes huge? So is it always about the target size and the distance, or something else comes into picture? Basically, what might come into picture is the choices. Out of how many stimuli, you have to choose one. That always comes into our mind. We become slow if we are given a lot of choices. We are human beings. At first we want a lot of choices, and when a lot of similar hierarchy choices is given to us, we ourselves get confused, and it takes time for us to decide which one to go for. Okay. So we get overwhelmed with choices, and therefore there is another model, another additional cognitive model, which is called Hicks' law. Not sure whether you have heard about this. The earlier one which I was talking about, that was trying to model the movement of your hand or finger, physical movement, motor movement. This is something which is going in your mind. It is trying to model the human choice. When a lot of choices are given, the reaction time which you would take to select something. So that's Hicks' law. What it says is, of course, by our experience, we know given more number of choices, it would take us more time. What additionally Hicks and Hyman has done is they have done a lot of experiments in this kind of setup. They have electronic circuits wherein they ask their participants, their subjects, to one by increasing the number of stimulus and see how much time they would take to light a particular bulb. What they have defined is, it's defined based on this kind of equation. It says that the number of targets, number of options, if you increase, it becomes logarithmically difficult or logarithmically more time taking for you to make a choice. Again, one would say that it also depends upon who the user is. Right? I would be able to take up decisions out of 100 in the same time which my grandmother would be able to take within 10 stimuli, because we are two different users. Because my cognition level is higher, my IQ level, just for the sake I'm calling this as IQ, but there is something which is there in probably me, which is not there in my grandmom, with which I can make fast reaction times. Okay. So all it says is, given a particular user, how he or she would perform is what is defined by this particular law. Someone who has higher IQ or who is fast would always stay as fast. But given more number of choices, that person will also get saturated. The question is, does it also apply to every choice making? No, there is a limitation. Hick-Hyman law applies to things where it is time critical. You are making a very basic decision. You are not thinking too much, and then there are too many options, such as there is a big panel and you have to decide what action or what control you need to take. Therein you apply this. It doesn't apply where you get a menu in your restaurant and you need to choose out of all of these burgers which one I want to have, because that's not a basic decision. You are thinking too much. It doesn't apply to that. So what we learned is it depends upon the number of choices as well. But is it only number of choices, or there is something else happening in our mind? The question is, given more number of choices, we will be slow. Given less number of choices, we'll be fast. But is it only number of choices, or there is something else? Let's do an exercise together. Let's see. I'll try to challenge your cognition. Let's do an exercise while you are seeing. I'll show something in the screen. Try to recognize, try to remember, and let's see how it works out for all of us. All of us are good human beings. Learn it once. So, I'll tell you, you can anticipate that there will be some letters which will be popping up in the screen, and we'll just do it for just 2 seconds and see how many we can remember. All set. Here you go. What do you remember? Try. Okay. What do you remember? Very great. 6. Crude. 5, 6. Something. Let's do it once again. Done. 7. It is improved slightly. Let's do it once again. That's it. What's the response this time? Much better. So something else is happening. It's not just the number of choices. It's not just the number of choices. I have just played out the same letters, but these are structured differently. So the number of choices do matter at one level, but beyond that, it's also about how it is presented, how it is segregated, and how it is well categorized. So if the categories are in such a way that it's easy for users or human beings to understand, generally if you can relate it to something, you have related it to BMW, FBI, you can relate it to something, it's easier for you to react on it faster. So in design, that also is played well. Think of these different websites which you have definitely seen, many different types of designs which you have seen. In some websites, you would see menu which is very, very long. They would play out all different options in the menu. And then there are much structured ones where you would keep at different levels hierarchies. So one of this is flat hierarchy, the other one is deep hierarchy. Both of these works. It depends upon what is your real world problem, who is your user, what they would be adapting to. So these kind of psychology of human beings do play a role, and if the designers are, or the technologists are aware of it, they can play that better. Question again is, to our reaction time, does it always stays the same, or does it also change? Yeah, one of the things you would say is with more and more practice, if I would give similar puzzle just like the last one 10 or 20 times, suddenly you would see that you would become faster, your reaction times become faster. Because why that happens? That's right. Yeah, there are a lot of complex phenomena which happens inside the brain, with which you are finding out shortcuts. You are able to remember things. You are able to remember patterns. You can anticipate things, and few of the things which becomes your muscle memory as well. Yeah, there is a question, sorry. Yes. Yes, conversation agents would work in particular specific context, right? It's not for mainstream. I mean, everybody can use it, but conversational agents are for a particular purpose. Like websites would always stay. It has been there. There are a lot of other things which plays out in the websites. Say, for example, there are companies which make ad revenues out of websites. Unless user browse through it, how would you know? And therefore, important things at important places, you would have better footprints of the user, and therefore you gain revenue out of this. Yes, the technology is changing, but few of the things would always stay. It might change in future, don't know. But yes, there are a purpose to those websites which has always been there, and it has earned revenue for companies. Okay. Question, the response is not from Google point of view, by the way, again. Okay. So we are talking about the reaction time and how does it change. There are a lot of complex phenomena which we just discussed, which is happening inside our mind. It's very difficult to identify and define what is happening, why we are getting faster in certain things. The question is it possible to model those? Actually, everything cannot be modeled. We can bucket few things and try and see if that represents a human way of working. This is another one which is called power law of practice. Probably you might have heard about this a little bit. It is obvious thing that more practice we do, we become faster in certain things. But through experiments, this has been proved that it has an exponential law, which means in this equation, all that this says is if you are trying something very early, you gain a lot of advantage very early. You become faster very early. Yield is high. But slowly, if you practice more and more, you would slightly saturate. Your performance would saturate at some point of time. So that is what you call as expert to novice, novice to expert behavior. And this is a continuum. It is not discrete. Nobody is an expert. Nobody is a novice. It's basically every user of a product out there is in some place in the continuum. So power law of practice defines that. So let's take a pause here and see what we have learned quickly, and then we would switch gears and talk more onto the research problem. What we have learned is a methodology, which is cognitive modeling. We learned there are 2 or 3 basic methods. There are a few more methods. I'm not dealing with all of those. We learned how to model the motor movement, which was Fitts law. There is another one which was trying to understand how people react to certain things, Hicks-Hyman's laws, and we also learned about the power law of practice. More practice you do, faster you become. Based on this, all that is theory. Let's understand what is the application of this. Let's apply cognitive modeling approach to something which I have worked earlier, and this would give you an idea how these existing models can be customized or used as is for real world problems like this. I would now introduce to the research problem of Indic language keyboards. This is a playground which we use to apply different methods. And why specifically Indic language keyboards? First of all, let me ask you guys in this room, how many of you in your mobile phone, specifically on mobile phone, do you use any other typing language than English? Which ones are? Tamil, you're typing in Tamil language. Yeah, using Indic language. Oh, great. Oh, great. Great. But still very few. Not everybody. Some people are raising their hands, but they're not confident. Probably the speeds are less and they're trying out still. Cool. Yes, this is something which any talk we make from our lab, we always ask this question to the audience, and we always see it's just not more than 5% people do it. Fine, because we are here, people in this room are the ones who know English, and it's obvious that people would prefer English because of communication, day-to-day life. We prefer that. But why Indic language? Indic language is for those people who cannot do like this, just like us. Because there are approximately 50% of our population in that level who are literate, but they are not English literate. They can write a language, but they cannot write in English. And also a lot of recent reports says that a lot of such users are coming online of late. And in few years, you'll find more number of those internet users. I'm talking only about India. Forget about few other countries. There might be other countries like Mexico, Indonesia, Malaysia, Bangladesh, Sri Lanka, wherein you will find such type of users who would be less English literate. So it's important to design for them, because if those users are not able to do typing in English, and if they are using mobile phones, actually they cannot do anything. Basically, they cannot send messages, they cannot shop online, the basic things which we do every day. They cannot even save a contact. So the question is why really Indians do not prefer to type in Indic language. I understand for people like us, but a lot of other people who do not know English, they still attempt to type in English, even with broken sentences. It could be also aspirational to some extent. Speaking in English, at least in India, is aspirational. People do that. But I'm just questioning it from the other side of it as technologists or designers. Really, is it that they really lack the tools to type in English? Have we not provided them good interfaces to type? Is that the problem? Let's understand what could be the difficulty. One of the difficulty, you would really realize, because you speak these languages, is that English is just 26 letters. You type what you get. It's alphabetical. Here you have vowels, conjuncts, consonants, 64 letters in Devanagari. There are a few other languages which will have more. Very difficult to type. First of all, very difficult to write for many people, even if they are literate. Second thing is the way it's composed, like it's alpha syllabary, it's Abigaud style of writing or typing. So which means you select a consonant, you take a matra or a vowel modifier to it, and that becomes a syllable. It's not like in English, you can spell out a word directly. So there is a lot of things going in your mind when you are doing this. Okay, when I'm saying this, remember what we learned in the first part. There are a lot of things which goes into our mind while doing this. We are thinking about our reaction time, how things are segregated, how we are choosing, and because of those reaction times, typing becomes even more difficult. So there is a challenge. The
second largest language in web content, they also have,
yes.
But Chinese have kind of problem. How are they managing the
Chinese pinyin, Japanese kana, some languages, kanji, right? So these kind of scripts are very much optimized to some extent. They have optimized those scripts for digital world as well. Their keyboards are in such a way that you can type faster. Specifically pinyin. So pinyin is basically a symbolic language. For instance, if they want to spell out something, they would describe it literally. Like for spelling out sun or something, sun, they would actually make something which represents sun. It's symbolic language. And when you have those characters, specific characters which can compose your set of grammar of your all letters, it becomes optimized for you to type. And again, another part which I said, it's also aspirational. They are trained to do that, specifically Japanese, Chinese, and Korean, other Asian languages, which are difficult, more difficult than Indian language. But they are optimized, and people are, yes, sir. This is brilliant idea. Actually, yes. In that way, Indian language scripts are well defined. They are kind of, they have a rule. Like if you spell out k, kh, g, gh, all of these sounds are coming up from inside. Then the next letter is ch, ch, th, ch, ch. So all of these sounds are coming up from your different parts of your vocal system. If we can make use of that and try out, say, ASRs to understand that part, probably it can do miracles. But I'm
big point here. And Cantonese are both tonal languages. So in addition to being representing pictograms,
this I did not know. This is a great information.
Cantonese has 7 tones, so the same word uttered in different tones means different understanding here. So in addition to being pictorial languages,
this is a great information. in any case, all of these are more optimized than English, definitely. More rich than English. We can make use of those nitty-gritties of this language, how these are originally designed into digital world probably. Probably this is the time when we can make use of those things. Great idea. Yeah, so there is a lot of challenges. Speeds are less. Accuracy is very, very low, and this is from a lot of research which has been done in Indian language compared to all of those research done in QWERTY keyboards or English language keyboards. Learnability of these languages is very difficult, these kind of keyboards. So these are all different challenges. The biggest challenge, however, which, yeah, right. Great. So today, during the lunch, I was talking to Professor Murli as well on this topic exactly. The richness of the language in terms of the grammar itself is different. Compared to English, Indian language, specifically Hindi, Marathi, few specific Indian languages are so rich in terms of its vocabulary that the root words itself would generate a lot of different words. So therefore, the prediction algorithm which might work for English language, the basic prediction algorithm, that itself might need to be changed probably. That also needs to be checked and see. Again, the size of the words are also different. The English words on an average are 5. That's a ballpark figure people say. Indian language, different. In Devanagari, they say it's 3.5. The size of the words are smaller. In Marathi, it's longer because it's more of an agglutinative language. There are 3 words mixed together and that is spelled as a single word. How would you get that as a prediction? Again, bigger the words become, we don't know whether that becomes a popular word or rare word again.
That problem actually is German. German has the same problem, right? Many words put together make one big word.
This is again agglutinative language. Even Turkish is such a language. But it's agglutinative, but I'm not sure. I'm not an expert in that area. But probably the size of the vocabulary they might have taken care. Being agglutinative does not mean the size of the vocabulary is also huge. But I don't quote here any. I have not researched in that area. Yeah. So the biggest problem.
Oh. So you just string words. Indian languages, the word itself changes. So the root remains the same. The same algorithm.
Again, the question is, we presented one paper 3 years ago in CHI, where we kind of demystified that prediction. It always does not help. So in English language, and it is a general perception for all the users that if you have prediction while typing, if the user starts selecting those predictions, they would become faster. Yes, for English language, and they have done a lot of experiments for last 10 years to make it a fact. But when we did this for Indian language, the results were reversed. We found that our users in a longitudinal experiment were getting slower. Because where they are getting slower? Every time you type in a letter and you know that there is something in the prediction which is going to come, you would waste time looking into it, and then you would find that the prediction is not working out because the search space is huge for your word. You would waste time. You will then attempt the second letter, and then again you will go back and see. So that was wasting the time. Instead, for an expert user who is kind of expert again, who can type slightly faster than these novice users, for them, typing it out directly without use of prediction, ignoring the prediction directly, was working out fast. So, yeah, depends upon again the language and how good the prediction is working for you. Yeah, so I was talking about all of these different keyboards which exist. When you type and search for, say, Devanagari keyboard, which I was trying one day, I found 200 different Indic language keyboards. Only Devanagari. I'm not talking about Tamil or Kannada or Gujarati or. And when you open each of these, this will have different layouts. Some of these use different interaction techniques. Some of these have also applied prediction. Some of these have multiple layers as well. So you have few letters at the first layer. You press a button, you reach the next layer. The question is, just like in English language where the QWERTY is a de facto standard, in Indian language we don't have one. Which one to follow? I don't know. Which is a good interface, good layout? What kind of interactions are faster? So that is the problem statement with which we did some research here. One of the way we tried out early was to try and experiment one by one all of these keyboards, but there was no end to it. And when you end up having such kind of problems, I spoke to you early, we tried out simulations. If you can create models how people would type, probably given a new layout, I can find out how efficient that layout is. Not on mobile phone. This work is primarily on mobile phone. Again, people who do that as part of their job are trained to it, which means they have learned typing. So somebody who is typing news on, say, Kannada, they would be anyway experts in that. We are not counting them. We are talking about mass users, mass adoption of these kind of keyboard layouts. Right? Why are we really thinking about having an efficient keyboard? This an hypothetical situation. Like if I can save having a very good layout, if I can just save 1 centimeter of my finger movement just to type one letter, think about how much impact we can get. This is just a hypothetical situation, just to show that how important these keyboards are and how important it is to optimize these keyboards. Right? Our research problem, if we wanted to understand what defines a good layout and what defines a good interaction mechanism for keyboards. So there are all of these keyboards and we consider this to be black box. We try and understand that there are different performance parameters as in accuracy or speed, which can be modeled based on few base parameters. Base parameters like the layout of the keyboard, the interaction mechanism which the keyboard has, the size of the keys, where the keys are placed, and what type of text needs to be typed. Okay. Language complexity also plays an additional role over it. So this becomes kind of a modeling problem now. You have a set of variables, you have a dependent variable and a lot of independent variables. Defining a relationship between x and f of x becomes a cognitive modeling problem, and that is what we tried out. But there are many aspects of typing or text input. Somebody already mentioned about correction, auto correction, or word completion, word prediction. That plays a role. Then which finger are you typing? Are you using an index finger to type, or are you using one thumb, or you are using multiple thumbs to type? There are different ways people type on phone. Then what are you typing? Is somebody dictating you something and you are typing, or you are typing free flow? Because the performance would really differ. Then what type of script this is, and in the end, what type of user somebody is, what level of experience the user is. Okay. Based on that, you can create performance parameters. So there are so many different variables. It's very difficult to do research in this space. So first thing is, when we get into this kind of problem, we optimize. We try to scope our research and say that this is the boundary of my research and I would do this. So the research which we did at present, which is already done, is we tried modeling three things: the keyboard design, the different touch gestures on the keyboard, and different levels of practice or levels of learning of the users. We try to model these three things in terms of the time performance. The way we approach this is by breaking the typing. What is typing basically? We tried and approached typing by breaking into micro actions. What are the micro actions? We are moving our finger from one character to another character is one part of it, which involves what? Motor movement. And then we are thinking, we are reacting to something, we are finding out something, we are searching something while doing this. There are two components. One is motor movement component, the other one is something going in our brain, like a lot of these things. We don't even know. That's why I put a dot. We don't know what is going on in our mind while we are typing. Probably we can bundle them together and try and model something. So we learned. Yes, typing as an action and swiping as an action. In terms of motor movement itself, these are two different actions. For tapping, one alphabet per gesture, because swiping, if you have used Google's swipe gesture or some such keyboard like Swift key also has that. What also happens is while you are swiping, there is some prediction algorithm which is going on in the system itself, which is trying to recognize what you have swiped. So it's not only humans' performance. If you have a very good algorithm which learns what kind of words you would use and based on your history it can predict words, it becomes faster, it becomes accurate. So even if you make shortcuts, it would still get you right one. So basically then you are modeling two things together, the human performance as well as the computer performance independently. So it's, while doing that action and in an empirical study, it's very difficult to segregate both of this. What is the performance, how the human is performing, and how good the computer is or the algorithm is. So that was one of the situation which we got into this research. We tried controlling that by disabling the prediction which goes in the background and then attempting to model only human. So again, natural behavior, in a sense, there could be multiple reasons for it. There are multiple intrinsic experience one would derive as a user. Whether somebody is interested to type fast, whether somebody is interested to type accurate, or somebody is trying to learn fast. So there could be multiple things based on which a user would actually take a decision, calculated decision. Okay, so when we divide into macro actions, the typing, we have two things primarily. The motor movement thing. We know how to model motor movement from our first part. We know Fitts law was the one wherein we did this kind of experiment to understand how movement from one character to another character, how much time it would take. If I separate out those characters to a farther distance or reduce the size of those keys, then probably my movement time would change. The other thing which is going in parallel is the cognitive time, which means your reaction time. And that can be modeled using Hicks law, we know. And power law of practice would give you that more and more you would search something, you would learn that where the location of those keys are and you become faster. So you can model that by power law of practice. It would have been easier if this was the scope and we were modeling only, say, English language keyboard. But our problem was different. We wanted to model Indian language keyboard. Therefore, we tried and tested and found that Hicks law model was not working for us because there are different strategies people would take, and the composition of Indian language itself is different. When you have already typed a consonant, that is the time you would look for a vowel. Otherwise, vowels are of no use in your. There are few keyboards which takes benefit of it. As soon as you type a consonant, the keyboard will pop up only vowels, only vowel modifiers. Consonants are gone at that point of time. So how to model those kind of phenomena was a difficult question. One way to do that was we did a lot of empirical study. Why don't we bucket everything together, separate out these two parameters, motor movement, and do a lot of empirical study and see what kind of phenomena we see. We did this experiment on keyboards, similar to Fitts. Exactly this was an experiment, a mundane experiment wherein we asked user to type between multiple keys, stroking across different parts of the keyboard, diagonal, different angles, all angles, and see what kind of performance they make. Then we did another experiment with few users whom we stress tested to a longer duration so that they saturate at some point of time. So we asked them to type in just two master phrases with a combination of all types of characters, that those master phrases were created in such a way that that has all sets of characters, so that we learn that how much time somebody would take to move across different parts of the keyboard. So something like this, we did this experiment. In a lot of these experiments, you would see young kids. There was a purpose, because who on earth will do an experiment with you if you ask them to type the two statements for 400 times? So we did this studies in government school. We also got a lot of users with whom we can do longitudinal study. There's another purpose for it, because see, if I ask people in this room to type in English language, it would take some time for you to unlearn something what you have learned on English keyboards. You would have to unlearn, and then that would interfere. This kind of products are for people who are semi-literate. I would call semi-literate users are those users who have, say, 5 or 6 years of formal education, and beyond that they have left education. So they are literate, but they cannot write in English. And therefore we picked up those kids of those age level. Probably we can operationalize their level of memory or their level of learning. Yeah, so it is interesting question, quite deep. We don't know. I don't know, because everybody knows some skill. And if De Jong says when they have done these experiments in 1950, they might have taken some subjects and did these experiments. And whatever their experiments are, probably there might be some users who would know some skill, and based on that also they kind of saturated at some point of time. The fact is, probably if you can discount out few number of trials initially, but after that you would actually follow that power law of practice. So in general you would do that, and we also found that in our experiments when we kind of stressed people. There were users who kind of are used to mobile phone. They know how to touch, and then there were some subjects who have seen a mobile phone, a touchscreen phone, probably their parents' phone, but they have never used it. So the confidence with which somebody was touching the screen of a phone itself was different. But you discount out for say 10 days of practice, and after that you start collecting real data and use it for modeling. No. Yeah, so off-the-shelf keyboard layouts were good enough for us, because we picked up few keyboards which are popular, includes Google Indic keyboard. There was a keyboard called Swar Chakra, which was designed in IIT Bombay lab. We tested that as well. Then we picked up which is called Inscript keyboard, which is the CDAC, which is designed by CDAC, and that is called as standard, but it's very difficult to use again. We use different keyboards which has different interaction styles. Few of these have slides, few of these have pie menu. So when we have a few keyboard samples which had all sets of these interaction styles and different types of layouts, that was our test sample. We controlled the size of the devices for this experiment, otherwise it would deviate. But if you remember, I would say, when we were speaking about, say, Fitts experiment, actually the sizes do not matter. The size of the target might matter, but what the equation says, you are dividing your distance by your size of the target. So on a smaller device, you have your targets very close, so you are saving your distance, but the size of the keys becomes small. But still, if it is a ratio, you are still the same. But we did this experiment on a low-end smartphone device, 5,000 rupee smartphone device, again because our user base for Indic language is not people like you, probably people who are semi-literate, and they would use that kind of keyboard. So that was conscious. Yes. Yes. Oh, that's a brilliant question. I mean, yes, many people ask this question, and anybody who presents this, they are getting this particular question. See, during those times, those experiments were done on physical devices. True. When HCI came up as a discipline, during research, earlier, I'm talking about research which has happened around 10, 15, 20 years ago. During that time, they tried and tested this again. Keyboard happened to be one of the test playground where people have done on English language, they have tested Fitts law, whether it works or not, and they have kind of customized it as well for keyboard. Those laws are very generic in nature. You have seen those, the equations are in such a way that it has constants. Yes, the coefficients would change. You would move from a computer screen to a mobile phone screen to a smartwatch. Probably your coefficients would change, but the law would remain same. And therefore, one of the reasons was why we were doing these experiments. We could have actually followed those coefficients which somebody has done on QWERTY keyboard and apply this. It would really change because the users are different, the layouts are different, and therefore the coefficients would be different. And therefore, in order to model something for Indian language, we'll have to find out these coefficients and do those mundane experiments again. But what we have in the background is, yes, a law which would anyway hold. So we already have an equation, we would try to fit into it. So we were talking about the application part of it. We did experiments, there were 3 experiments. What we got out of these experiments? One of the experiments was to tap between keys. What we did is increase the number of targets. So Fitts did this experiment tapping between 2 points. We tried doing n points. We tried doing 3 points, then 4 points, and 5 points. Try to see that can we replicate the typing behavior. So if somebody is given to type something and there is an expert behavior, somebody has become an expert. So you are typing in a QWERTY keyboard, you would tap from key to key. Is it similar to tapping between n keys? So can I use Fitts law with n as my tapping point and extend that law for typing? So when we tested it, we found that yes, it works out because we stress tested these users and found that, so you would say that this orange color is the curve. Basically, what it shows is it's the typing time. More you do, increasing the number of level of practice, you become faster, so your time reduces. At some point of time, your experience or your expert level speed would come and you would saturate. You would start performing at a level that you are tapping between keys, tapping between n keys, and that is what we found. In the third experiment which we did, we also found that there are a lot of novice users who started slow, and with lot of repetitions, we were able to understand what is their curve. Basically, this is following the power law of practice curve. Right.
Characters in the language have a power law, right? Some letters are used much more frequently. How is that?
I'm coming to that. It's part of this one. I'll maybe in 3 or 4 slides I'll show what exactly is the behavior for each of the characters. This is to answer your question. So this is one of the keyboard which we used as sample. This is called Swar Chakra, designed by IIT Bombay lab, our lab. This heat map, what it shows. So the red heat map, what it is these are just times. Times these characters were hit by so many users. How much time on an average it took. Darker the red color, faster they were. So when we realized, we found that few characters, few locations in the keyboard, these characters were getting undue advantage because of that location. So for example, consider this as a layout. You would know where ka is. It's an alphabetical layout, and you end up writing a word which starts from ka. You know where it is because it should be in the beginning. So therefore, it's faster. Then there are few corner advantage somebody is getting. Few characters in the edges, in the corners, those were faster to find and type because people were able to find that faster. Then there is something else going on. There are popular characters and there are less popular characters. So you gave them a test sample to type, a corpus to type, and those corpus anyway has words, and those words definitely the popular characters will appear more, and people were getting faster on those. People were learning that very fast because again, power law of practice. They were typing those, finding those characters more and more, and they were getting faster. The point which I want to make here is people do not learn the keyboard in one snapshot. On a practice, people would learn parts of the keyboard at different times. At few points of the keyboard, they were learning faster. Few letters in the keyboard, they were training faster. Few of them still they were slow. So why don't we make use of that? We put popular characters at those portions of the keyboard where anyway we know that people will reach faster, or they would be able to recognize those characters faster. That was one of the things. So what we did is we divided the whole keyboard into different cognitive zones. That these is a zone of say unique characters. This is a highly frequent character and things like that. And trying and modeling that using the power law of practice. Again, power law of practice, trying to understand each part of the keyboard, how fast they can learn. Let's not go into details of this one, and it will involve. So consider that we tried understanding each type of key, each portions on the keyboard, how fast people can learn. Similarly done for a few other keyboards as well. Created cognitive zones, time zones for each of these keyboards like this. Came out with the model. Again, through model, we always try to see how much is the accuracy this model is trying to achieve. Basically, how we do that, we'll have say 70% of the data to train the model, and then keep 30% of the user data to just test the model and see. So basically what this shows is your actual versus predicted for 3 different keyboards. You could see that the accuracy of the model came out to be approximately 90%, which means that for few keyboards which we have tested, we were able to predict the speeds of any typing by any type of user approximately with 90% accuracy. We tried applying it back and see how it works. So this is a sample. So there is a sample phrase, Sakadi ani Ratri. This means in Marathi, morning and night. Okay. This sample sample phrase which was given to the users during the experiment, and they typed it out. And we were able to replicate the same thing using simulation and try and see how much good we are, our models, how good it is. And we were also able to see which keyboard is performing well at which letter. So we were able to check at the micro level that which letters each keyboard is losing time or gaining time. So for example, these 3 curves represent 3 different keyboards, sample keyboards, and we see that how fast, and this is basically cumulative time of typing this. This is in milliseconds. While typing what, people were losing time, we were able to understand. So through this, we were able to understand that how we can compare multiple keyboards for different types of typing, for different types of use. A little bit about what contribution this research brings in. Specifically about this research, this tries to model the motor movement. We know how to model that through Fisk's law. We tried doing this for Indic language keyboards. We tried developing models for new touch interactions. What we covered was tapping between keys, sliding, long press, these kind of interactions we were able to model. If there is a new keyboard somebody wants to design which has these interaction mechanisms, one would be able to use these models directly. We were able to define different cognitive time zones where which portions of the keyboards are good to keep important characters for different layouts. And we were able to develop some models for learning. Learning as in a user is a novice, which keyboard is good. A user has 3 hours of practice, then model can tell you which keyboard would be good for him. And then overall, we were able to systematically provide a method of modeling of typing times. Okay, so this is my last slide, almost 1 hour 10 minutes. So my hope out of this session is, first thing we started with from the dialogue which Don Norman made, is that technology should be, again, always designed keeping human capabilities in mind. I am adding capabilities here because all human beings have some capabilities, and since human beings are basically some kind of a sophisticated biological computational devices, machines, we can to some extent measure their performance and predict to some extent their behavior. The last thing out of this one is I would like to entice all the researchers, students to explore this space, cognitive modeling, an approach. It's an approach to design for technology, and do contribute into this research area. We are still actively working on Indic language keyboard in IIT Bombay with Professor Anirudh Joshi, and therefore, if you are interested to work in this space, collaborate, you know whom to contact. Thanks a lot.